We are doing our final presentation on the beam project, and we are in Dr. Maier's class, Engineering 141, and we are the group B5. And my name is Alexis Kaiser.
I'm Rachel Johnson.
I'm Dinko Carr.
And the reason we are doing this project is because our engineering firm, GE Tigers, has been contacted by a biosystems engineering company that's been researching to measure the amount of the suspended sediment in rivers. Our instrument that we want to find will be hanging from a long metal bar over the water, and as the water flows by the instruments, the resulting drag force will make the bar bend. And our team is to conduct tests on metal bars and conduct and determine a mathematical model that can be used in the field to determine the optimal instrumentation configuration. And that is the reason why we're doing this project. For our mathematical model, we wanted to study the behavior of the beam, and we wanted to determine the relationship between the beam stiffness and then the other variables. So we assumed there was a power relationship of the variables that made up K because of the equation that was given to us and our recent knowledge. But we do not know the values of the exponents for M, N, P, and Q. And so given the equation, we figured we should solve it like any other algebraic equation. So we wanted to set one variable as the unknown and solve with the other ones being constant. And then this led us to determine the different beam lengths, and then several masses would be applied, and then we would measure the deflection, and then this would allow us to determine the exponent of Q. And that is how we started our mathematical model.
These two graphs are the length graphs. The one on the right shows the comparison between length and stiffness, and the one on the left shows the comparison between force and deflection. These two graphs are the width graphs. The one on the right shows a comparison between width and stiffness, and the one on the left shows a comparison between force and deflection. These are the thickness graphs. The one on the right shows the comparison between thickness and stiffness, and the graph on the left shows the comparison between force and deflection. These two graphs are the graphs of modulus of elasticity. The graph on the right shows the comparison between stiffness and elasticity, and the graph on the left shows the comparison between force and deflection.
This table shows our calculated values and the actual values of the exponents that we talked about earlier. Our calculated values from the first part of our project were originally 0 for M, 0 for N, negative 2.9 for P, 4 for Q, and 2.02 for C. After we got back the first part of the project, we went back and fixed it to get the actual values, which were M equals 1, N equals 1, P equals 3, Q equals negative 3, and C equals 0.25. We thought there were some errors. We figured out there were some errors from our first part, and the list of some of the errors it could have been. We could have had some measurement errors when we were taking our data, and there's a typical uncertainty for a meter stick of plus or minus 0.02 centimeters, so that could have played a role. And we also measured our deflection with the two beams on top of each other, and some groups did them right next to each other, and that also could have played an effect on how an error in our calculations. There also could have been some conversion errors in calculating from meters to centimeters or grams to kilograms or whatever else we had to do conversions. And there also could have been programming errors in our actual program to help calculate what our N, P, Q, and C were. This slide shows our predicted and achieved loads when we were given deflection with certain parameters of the beams. We plugged the parameters into our program, and for the first beam we got 26,800 grams predicted to get a deflection of 1 inch, and it actually turned out to be 1,460, giving us a percent error of 94.5. The second one, to get a deflection of 1 inch, we had a prediction of 27,380, and the actual was 489 grams. The percent error for that was 4,499%. And to calculate our percent errors, we did actual minus theoretical over actual times 100. And we know what we did wrong in our program. We used trendline equations to help predict the load that would be required to achieve a certain deflection, when we should have used the big long equation that was given in the very beginning with our exponents, solved for the K, which was stiffness, plugged it back into P equals K times deflection, and then using that we could have solved force equals mass times acceleration to find the mass. This slide shows when we were given a certain load to apply to certain beams, the prediction or the deflection that was predicted by our program. And for the first load and the first beam, the prediction was 0.8151 inches, and when we actually tested it, it was 1.125, and our percent error is 27.5. On the second beam, we predicted 0.858, and the actual was 0.938 inches, and the percent error for that one was 8.5. We figured there could have been some error in our programs, maybe a few decimal places off, some problems with our trend line relating back to the first time in the lab when we were collecting data, but there also could have been some measurement data errors in testing it to find the actual deflection this time around, and so that could have played a factor into our errors.
Our main concern was the cost of the optimal beam because we wanted people to actually be able to purchase and use the optimum beam. There are drawbacks to this theory, but we put ourselves in their shoes and we wanted to make this project as useful as possible to the people we're trying to help.
Choosing a stainless steel beam because aluminum beams, although they do not rust, they will corrode over time because of the air exposure. This will cause our product to be less productive over a long period of time.
The reasoning behind why we chose to use stainless steel with the size of 0.25 by 0.25 inches is because it gives us the area that is a square. Based on our calculations of deflection and load, we wanted the least amount of deflection, so we chose the beam with more square shape. And because of our results, the longer and thinner the beam is, the more deflection it gives, which makes it less optimal. And the shorter and the wider the beam is, it would provide less deflection, which makes it more optimal.
Although we did eliminate aluminum beams from the start, the same concept applies with the aluminum beams that were calculated within our program. We would have wanted the beam with a similar length and cross-section and width.
For the first part of our instrument evaluations, we set up a table for instrument, the estimated drag force, price, pros, cons, and other, and we set it up as a table so it is easier for the viewer to see right in front of them and compare directly all the instruments. The first instrument was a turbidity meter, which tests the clarity of the water, and then the price was on the higher side, and then a positive of this was that it was very accurate, but it also can be done, it's been done getting up time just to look at the water. If it's a little murky, you know to be cautious, or if it's clear, it's going to probably be okay to drink. And then I guess it's not very practical because you can do it by looking, and because of the steep price and the higher estimated drag force, we chose not to use the turbidity meter. As for the portable sampler, basically the name says what it does. You can test samples of water, so it is portable, which is a positive, but again, it is very pricey, and it has a rechargeable battery. It can charge within 12 hours, but we are not sure how the power and electricity system works for where we're trying to build this. And then it is portable again, but it is better for shallow wells and surface water, which we will be working in a river, so it may not be optimal conditions. To continue the instrument evaluations, we started with the velocity flow meter, which did have a higher estimated drag force, and it has a 365-day battery life and can withstand submergence, which is very important to us because we don't know the conditions of the river. And then it is difficult to be able to use, but it also is able to collect the rainfall logging records, which is very helpful for the community to be able to see how the rainfall patterns change and go within the seasons. Our next one was the nutrient meter, which is only able to measure the ammonium and orthophosphate, which for the $250 price is expensive to measure only 2 nutrients. And then it's not very practical because we would want to be able to measure more of the products and the nutrients that are in it. As for the pH electrode, it had a very low estimated drag force, which was optimal, and the price was very cheap as well. And they were accurate and very quick readings compared to other ones that could take longer amount of time. And then a con or a negative is that it could be easily broken as it is glass, but it will give you, and it only responds to single charged ions, which could be a problem if there were more multiple charged ions in the water. Final result, we decided from our research and our program calculations, we have decided that the optimum beam and the instruments that we were going to use were the stainless steel beam, the 0.25 inches by the 0.25 inches with a length of 18 inches, which would be a cost of $10, and the velocity flow meter with a drag force of 4 pound force and a cost of $180, and also the pH electrode with a drag force of 0.5 pounds force and the cost of $35. And we did not decide to include a third instrument because of the cost and the higher drag force, because the velocity flow meter already has a higher drag force, so we took that into consideration.
We chose the stainless steel beam because of the no corrosion or rust, so it would be able to withstand any weather. And we chose the cheapest stainless steel beam, which we thought was very important to our company, seeing as we have some limited funding.
We chose a velocity flow meter because it seems to be most reliable, accurate, and the cost is more reasonable too. It is difficult to use, but the learning process can be passed down and one can train another in the village. The estimated drag force is high, but with such a valuable device, we can use one instead of two devices, having cost down and more effective and more efficient to use.
We chose the pH electrode because if the velocity flow meter fails or has a battery malfunction, which is very rare, but we must keep in mind as engineers that a second option is a good plan to have. The pH electrode is reliable and cheap, so it is a great second option. The estimated drag force is also very low, so it is an optimal instrument.
Thanks for listening!
Have a good day!
Go Tigers!